Good afternoon, everyone. Uh, got a question right off the jump. Do we need to attend class for the final exam? No, you don't. Um, the final exam should be during finals week, and there's no classes. So um, yeah, so I might have screwed up. I thought I had a thing on the syllabus about when the last lecture was, but I might have neglected to include that. Let's see. Last day of class is April 26th. Yeah. Oh, okay. Oh, then I made a mistake then. If classes end the 16th, then the last day of class can't be the 26th. So, um, yeah, yeah, it should be okay. So maybe yeah, I might have. Oh, it is the 26th. Oh, is that what? Okay, Joseph is saying it is the 26th. Okay, I'll double check that. But if I made a mistake on the syllabus, I'll fix it. But according to the syllabus, the way it currently is Monday, April 26th is the last day of class, and the final exam is April 30th, 4 days later, from 4 to 6. And that's a Friday anyway, so yeah. I guess we're getting into the home stretch here. The semester went by quickly. Okay. Okay, I have a few announcements for you. We have Project 2 or Lab 2 grades are posted. If you have a question about your grade or you think we might have missed something, please contact us. Charles did the grading this time, so it'd be easier if you send an email to Charles and then CC Philip and I on it as well. We're still working on the third project. We had to change our plans a little bit because it seems like we've been miscalibrating the level of difficulty on the projects. We had a very low submission rate on project 2, and it seems like you guys might not be getting the help you need on the projects. When we have the class in the lab, it's never an issue because you're in the lab and we're in the lab, we're walking around and we can answer questions right away and in person. But with these virtual courses, I'm getting the impression that some of you guys, when you run into trouble with the projects, that you don't ask because you know that even if you do ask, it's hard to interact over email. So I think that's the issue. So we're trying to come up with a different type of project that lends itself a little better to the virtual format. So we'll let you know as soon as we have that done. So there'll just be one more project. Sure, go ahead, Jackson. While he's typing that, there's something else I wanted to mention. Oh yes, quiz 6 is due today by midnight, and there was a typo on the answers on questions 9 and 10, which I have fixed. If you already submitted it, don't worry, I fixed it for you. But if you haven't submitted it yet, if you've just opened the quiz and you've looked at it and you haven't actually submitted it yet, take another look at questions 9 and 10. I believe I have those answers fixed. Yeah, I had to hack question 9 and 10, unfortunately, because a few of you already submitted it, and I apologize for that. It was just I had a mistake in my solution. I'll talk about it more on Wednesday, but basically the question asked you to calculate the delay for a 2-input NAND gate driving 2 other 2-input NAND gates, and in my solution, I messed it up because I calculated for a 3-input NAND gate driving 2 2-input NAND gates. So someone brought that to my attention, and it was obvious that that was the issue if you go to question 10, because question 10 asked about contamination delay, and there was the answers of question 10 made it kind of obvious that I had the wrong number of inputs on the driving gate. So, but I'll talk a little bit more about how to calculate that in this lecture too. And if you have any other questions about the quiz, feel free to email us. We'll try to get those answers back as soon as we can, because the quiz is due at midnight. Was there anything else? I think that was it. I think that was all the announcements we had. Okay, so let's see, where were we here in terms of the lecture? Okay, so last time we were talking about how these MOSFET transistors behave, and I talked about how they have one other thing. Yeah, there was one more announcement, sorry. I sent an email out last week with a link to a YouTube video that is the 611 lecture on CMOS. That lecture doesn't cover all of the topics that I'm covering in this class. I'm going into a little bit more detail in 317 as I did in 611, but that lecture does have kind of a different perspective on this, on some of the same material, particularly CMOS logic and how pull up and pull down works, as well as noise margins, which I'm going to talk about today. So if you've got some extra time and you'd like to just see the same kind of information presented in a more polished and produced way, then you can check out that video. When I recorded the lectures for 611, I did them offline asynchronously, so I was able to produce them much better than these lectures that are just kind of extemporaneous. So just wanted to throw that out there. Okay, so so the transistors have 3 operating modes: cutoff, linear, and saturation. And the cutoff mode is when the voltage on the gate doesn't meet the threshold, and so there's ideally 0 current that flows from drain to source. So that's that top term here. So this is the IDS, current flowing from drain to source, is 0 when the gate source voltage is less than the threshold. Then there's the linear region, which is where the current is beta times GS minus VGS minus VT minus VDS over 2 times VDS, which it should be what we calculated in the last slide, right? Sorry. Yes, yeah. Right. And the beta term is the mobility times the capacitance of the oxide multiplied by width over length. And remember that the capacitance of the oxide is the same across the whole chip. The width over the length is something that you as a designer choose when you're designing a chip, you're doing layout. And mobility depends on, there's only 2 possibilities for mobility, and it just depends on whether you're using you're designing an N or a P type transistor. And the mobility is twice as high for the N type as compared to the P type, which is why your PMOSs are generally going to be twice the width of the nMOSs in order to basically match the beta term. So you want the beta to be equal for both types of transistors. Now, one thing that I always felt was a little kind of vague was, why do we care about current? Well, the current gives us a, basically is, we want the current, we want the IV curve, the current versus the voltage, to be such that we have the lowest effective resistance for the transistor. Because as we're going to find out with the delay, when I talk about delay, the effective resistance is really important for the delay. So basically, the lower the resistance is, the effective resistance is of a transistor that's driving a wire, the faster it is, because the delay is essentially the resistance times the capacitance. So we try to get that resistance as low as possible. If you want a faster transistor, you can lower the effective resistance by changing the beta. So obviously the only way as a designer you have to do that is through the width. So you make it a wider, you make it a bigger transistor, you get more current and therefore less effective resistance and less delay. Okay, so right, so we had the cutoff, the linear and saturation. Linear and saturation mode is determined by the point at which the transistor channel gets pinched off, and that happens when the drain to source voltage is high. It actually depends on whether it's an nMOS or a PMOS. And an nMOS, it's when the drain to source voltage is greater than the gate to source minus the threshold. That's the saturation mode. So why is that important to understand? Well, because we looked at these curves, these IV curves, as a way to determine how a logic gate works. So we built an inverter by putting an nMOS as the pull up and a PMOS as the pull down, and then for different gate voltages. So we had now Vin is the input to the inverter, which is connected to both gates, right? So that's Vin, and then we have current that's flowing through both transistors is ideally is going to be equal, assuming that we have no load on the output here. And that's just because, whatever current flows through one has to flow through the other, because it's going to be, flowing down that branch from VDD to ground. So we looked at different input voltages, which determine the gate source voltage for both the nMOS and the PMOS. Now remember also that the source terminal on these transistors is the middle terminal, is the output, which is kind of weird because it means that the PMOS has the drain on the top and the source on the bottom, whereas the nMOS has the source on the top and the drain on the bottom. So they're kind of flipped, but they're set up to where the source is the lower voltage on I'm sorry, I screwed that up again. I always screw that up, sorry. Scratch that. The source terminal is on the top, rather, for the PMOS, and on the bottom for the nMOS. I always get that swapped. I'm sorry for confusing you. So the drain is in the middle. The drain terminal. So the source terminal, when you say gate source, the source terminal is the ground, or close to the ground for the nMOS, and is close to the VDD for the PMOS. So I apologize for that. The drain is in the middle. Okay, so what happens is, as you raise, like for example, in this case where Vn is 0, basically we're turning on the PMOS, right? So the PMOS, if you look at the gate source is going to be negative VDD up here. Is going to be actually for the whole thing negative VDD for this. I'm sorry, actually right here, negative VDD right here on the left hand side, because V out is 0. So V out is the drain. So and actually the gate source is going to be negative VDD actually through the whole thing, the gate source, because the source is connected to VDD, right? So that's always on VDD. And so what you're looking at here is, as you increase the V out, which is the drain, as you increase the drain, the transistor will basically start, you get this nice, you have this nice linear behavior here, as you have a nice strong negative gate voltage here, and so you can see you're basically in linear mode, right? But as you increase the Vin, now this is a little confusing. This is not 0.2 volts. This is 0.2 VDD. So this is 20% of the VDD. So if this were a 1 volt VDD, this would be 0.2 volts, and if it was a 2 volt VDD, this would be a 0.4 volts, right? I don't know what VDD is here. This is just an example. So this is at 0.2 VDD, and you can see that the the voltage is higher, and so you're not going to have as strong as a gate signal on the PMOS, right? So this would be gate would be, you know, say I don't know, say 200 millivolts, right? And so that would be you know, VDD minus 200 millivolts. So you still have a negative, you know, negative 0.8 voltage on there. But even then, this guy is still so low on the NMOS side that the NMOS transistor is in cutoff. So the NMOS is in cutoff, PMOS is on, but you're not going to get you're not getting as much current through it because it's, you know, its effective resistance is higher. And then as we continue to increase, now this is where we're kind of at the halfway point, right? So at this point, the NMOS starts to be above its gate source voltage is above the threshold, but it saturates. It saturates, right? You can see the saturation point is when we kind of linearly increase the current until we reach this point, and then we saturate. Meanwhile, the NMOS is also in saturation. Sorry, the PMOS is also in saturation. There's a blue one, but until you get to about this point, in which case it goes into linear mode. And so what you're looking for is when those lines cross. So, so skipping ahead here, basically what happens is that in region A, up here, is when the PMOS is in linear mode and the NMOS is in cutoff. But as you increase the input, you start to, you get to the point where you saturate the nMOS. And you can see that was what was happening here, is when we're saturating the nMOS, actually. Sorry, I screwed that up. Right here. Yeah, you see this is when, actually, well, this is a little higher, but you can see in this case, we saturate the nMOS over here. It goes linear and then it saturates at this point. That region, that was 0.4 VDD. So that actually, the input was still a little higher, or sorry, a little lower rather here at point B. But anyway, NMOS was saturated, PMOS was still in linear. And then we get to point C, and this is really the interesting point for us, because this is when the VN is halfway, VDD over 2. So that's about right where you have the 0.4, a little bit, it's between 0.4 and 0.6 VDD, right? But you can see that, you know, when you're at 0.6, both of these guys are saturated for most of the time. I mean, you know, it's a little different because we're at 0.6, but essentially both transistors are in saturation mode. And that's when you get to this really steep part of the curve. And that's when you're using up that's when you have the most current flowing through the gate, and that's where you're using your dynamic power consumption right there when it drops. So whenever you look at, like, if you remember from 211, if you remember the dynamic power consumption formula, hopefully you learned it in your, I'm not 211, sorry, 212. Hopefully in 212, your architecture course, you learn that the dynamic power consumption is the capacitance times the voltage squared times the number of bit transitions, or sometimes they use frequency. And that's the whole idea there, is that the bit transitions or frequency is you're measuring power lost during this time when both transistors are in saturation mode, because that's where you're losing, or that's when you're sourcing most of the current through both transistors. Okay, so that's basically how the inverter works. It's a little bit naive because, as I mentioned earlier, we're assuming this whole analysis is based on the idea that we're not sourcing any current out of the output. We're only basically assuming that the current coming down out of VDD is equal to the current flowing down through the NMOS to ground, and vice versa. So it's a little naive, but it gives you an idea of how these, how you'd kind of simulate the circuit. Okay. Okay. So then we talked about last time we talked about delay, and there's this notion of propagation delay, which is the time from when your input changes on a gate to the time the output changes. And it's measured from VDD divided by 2. So this picture shows an inverter. So you have an input. So the input goes from 0 to 1 and the output goes from 1 to 0. But there's a time difference between when the input crosses the halfway point and when the output crosses the halfway point. And that's your, in this case, the falling propagation delay, because the output is falling. Likewise, you have a rising propagation delay, which is when the input is falling and the output is rising, but the input crosses the halfway point and the output crosses the halfway point, and that's your rising propagation delay. And then there's also this notion of a rise and fall time. The rise and fall time are independent of the input. The rise and fall time only measuring the output. So you've got the fall time is from when the output goes from 80% of VDD to 20% of VDD, and the rise time is when you go from 20% of VDD to 80% of VDD. And then there's the contamination delay. So the propagation delay is the maximum, is the most time. It's kind of like an upper bound. It's the most time it would take for the rise or fall from input to output, whereas the contamination delay is just the minimum time. So the contamination delay measures, kind of like ideal speed, propagation speed through the gate. Okay, so now we want to figure out how to calculate those things. So the transistors have a capacitor on the gates. Now remember that the logic gate has an input or inputs, that those inputs go to the transistor gates. And the transistor gates are capacitors. And the diffusion areas, which is the source and drain of the transistors, it turns out that those are also capacitors because they are reverse bias diodes, but a reversed bias diode is also a capacitor. Now that might be a little surprising to you, because in electrical engineering you probably learned that a capacitor is two conductors separated by a dielectric. So a capacitor might be like two metal plates with glass in between, or a vacuum in between, or some type of non-conducting material, ceramic or whatever you put in the middle of the capacitor. The thing here, though, is that these are diodes. So how is a diode a capacitor? Well, the dielectric in a diode, a reverse bias diode, is actually the junction where the charge carriers move away from the junction where the P and the N type silicon come together. So when you try to send current the opposite way through a semiconductor, through a diode, the charge carriers repel each other, and you end up with what is essentially a dielectric in between, which is it's semiconductor that doesn't have any charge carriers in it. So that's what happens here. Now the thing is that delay is determined by resistance and capacitance. So I mentioned earlier that if you want less resistance and therefore more current, what do? You increase the width of the transistor. However, when you do that, it kind of backfires a little bit, because if you increase the width of the transistor, you're also increasing the capacitance not only of the gate, but as it turns out, the diffusion area capacitance is also increased at the same rate. So that kind of stinks. I mean, you try to get more current through the transistor, but you end up also increasing the capacitance as well. So you reduce R, but you increase C for the transistor. So that's kind of that's an issue you have to consider. The other thing is now I mentioned that the gates of the transistors are connected to the gates of the input. The diffusion areas, which are the source and drain, are connected to the outputs of the gate. So it's the gates are the input and the diffusion areas are the output. So when you're measuring propagation delay, you're measuring, you have to consider the capacitance that comes from, that's contributed by the source and drain for the output of one gate, and then that connects to the input of another gate, and the input has the capacitance from the gates, right? So basically when you measure propagation delay, you're going from capacitance of diffusion area to capacitance of gate. Okay, so the way you do that is, for instance, you consider like in this case an NMOS transistor. It has a gate, a source, and a drain. Source, and again, the source is on the bottom. Remember, the NMOS is the source is going to be on ground. It's going to be on the lower voltage, and the PMOS, the source is at the. Actually, it's flipped on here, but that's interesting. Yeah, the source should actually be on the top here. I don't know. I got this from the textbook. So you've got K, which is the represents the size, and so a K of 1 would be a minimum size transistor. Minimum is typically when the width divided by length, right? I have that right? Yeah. Width divided by length, which is part of the beta term, that's going to be 2 for a size 1 gate. Well, that's confusing. I know it's confusing, but when K is 1, the width is going to be twice the length. So if this is a 14 nanometer transistor, then the length would be 14 nanometers and the length would be 28 nanometers. And that would represent a minimal size unit 1 transistor. I mentioned earlier that the PMOS, the pull-up, the PMOS transistors, those typically will be a 2 at the minimum, right? Because you're going to have the width is going to be 4 times the length as a minimum sized PMOS. But the K value is still in relation to the minimum size nMOS. Okay, so I know sorry, I know it's a little confusing, but here's a picture of that. So typically you'll see like a minimal size inverter will have a 1 for nMOS and a 2 for PMOS, because the PMOS is always twice the size of the nMOS. The nMOS size 1 is the minimal size, which internally means the width is twice the length, but that's just encapsulated within the beta term. Okay, so you have to consider with these transistors, there's 3 sources of capacitance. There's the gate capacitance, right? There's the source capacitance, and there's the drain capacitance, which are the diffusion area capacitances. And then likewise, there's a resistance for the gate too. Now the resistance will be less as you increase K. So the resistance is divided by K, whereas the capacitance is multiplied by K. So you make a bigger transistor, you're going to multiply the capacitance, not only of the source and drain, but also of the gate, but you're dividing its resistance by K. So that it's R divided by K, and then you've got K times C. Now you might say, wait a second, are you telling me that the capacitance of the gate and the diffusion areas is all the same? Yeah, pretty much. Yeah, it seems unlikely because they're, well, for one, they're different sizes, they're different areas, they're different types of capacitors. But they're about the same. So you can approximate those as being the same. It's just K times C. And then now the capacitance for the PMOS is still Kc, but the resistance is different now. The resistance is going to be 2 times R divided by K. So why is that? It's because, like I said, K is relative to the nMOS minimal size. So basically, for all practical purposes, if you want the beta values to match, you want the resistances to match, you need to start off the PMOS transistors with a K of 2, which would give it an R of a resistance value of 1, 2 over 2. And that's what you see here. So you've got, like, in this case, you've got two inverters that are connected in series, and nMOS is size 1, PMOS is size 2, and that's going to give you a resistance of R on the pull down and on the pull up transistor. But the capacitance of the pull down is C, right? And the capacitance of the pull up is 2C. Okay. Now what's happening here is that to measure this total delay of a gate driving another gate, I'm only going to concern myself with the output of the first gate, meaning that I only care about the resistance of the transistors and the capacitance, but only of the source and drain capacitance. So notice how you see over here, I've got this, there's a capacitor on the gate input, but notice I don't have that over here on this bottom design. I don't have that because I don't care about the gate capacitance of the first gate, of the first logic gate, of the first inverter. Likewise, on the second inverter, the one that's being driven, I only care about its gate capacitance and not its source and drain capacitance, because I want to measure the time it takes from the time I connect either the pull up or pull down. I want to measure that to the time when I charge up the gates on the second gate. I know it's confusing because the transistors have gates, and these inverters are also gates. But the delay I'm measuring is not considering how long it takes to charge up the inputs to the first inverter, only the time it takes to basically charge up its source and drain capacitors. And then likewise, I only care about the inputs or the gates on the second inverter, right? So like I said, you're basically going to, you take away the gate capacitance of the first inverter, and you take away the source and drain capacitance of the second inverter. So the gate capacitance on the first one goes away, the source and drain capacitance of the second one goes away, right? But it turns out that you can optimize this even farther, because if you look at the source, so I got it right this time, the source terminal on the pull-up on the PMOS, it has a capacitor, but I don't, I can get rid of it, because in this case, because the source of the PMOS is connected to VDD, directly to VDD, then I can disregard this capacitor because both terminals are connected to VDD. So it doesn't affect me, right? Now that's only the case for whatever transistor is connected directly, in this case, to VDD, right? Now, if I have more than one of these transistors in series, then I can only delete that capacitor for one of them. So, but in this case, it's an inverter. There's only one pull up and one pull down transistor. So I can, basically I can delete this whole capacitor. Likewise, on the nMOS, on the pull down, its source diffusion area has a capacitance, but it's connected to ground on both of its terminals. So I can disregard that. So basically what's happening there is, for example, over here, you've got one of its terminals is connected to connected to, in this case, ground, right? So you'd have this terminal connected to ground. So this capacitor would be ground, and over here, this capacitor would be VDD. So I can disregard them, right? So what I end up with is this very simple equivalent circuit that has a resistor, and this is for pulling down. So this is assuming I'm measuring the falling Oh, wait a minute, make sure I got that right. So I'm pulling down, yes, I'm pulling down the output of this guy, which would actually end up pulling, which would, well, right, it would be pulling down the output. So I want to measure the fall time of the first gate, of the first inverter, right? So that resistance is to ground because I've turned on the switch that's pulling down. I've turned off the switch that's pulling up. So effectively, this transistor is a 1R resistor to ground. And then I've got the NMOS's drain capacitor and the PMOS's drain capacitor. And then I've got the gate, both gate capacitance of the gate being driven, the target gate here, the output gate. And so I've got 3 units of capacitance there, right? So all these capacitors are all contributing to the delay. So the propagation delay can be estimated. It's R, the resistance times the capacitance. So R times 6C. So it's R times, you add up all these capacitances, right? Now this would be, again, though, this would be for the falling time, right? Because I've turned on, and again, this is relative to the first gate. So how long does it take the first gate to fall? Well, I got to pull its output down. So I've got 1R of strength there, and then I've got all of these capacitances, some of which come from the output of the first gate, and some of which come from the input of the second gate. And so I add all those up, so the delay can be estimated as R times 6C. And so that's pretty much it. You just multiply your resistance times the capacitance. Now it gets a little bit more complicated though when you're dealing with gates that are more complicated than inverters. Okay, so likewise for the let's see here. I already showed that, right? Yeah, sorry, I went the wrong way. Okay, so let's now look at a 3-input NAND. So this is similar to the question I have on the quiz, except it was a little simpler on the quiz. I had a 2-input NAND. So the first thing you have to understand is how a NAND works. So NAND is a gate where you have nMOSs in series, and because you need to have the inputs all have to be 1, so you have to turn on all 3 nMOSs to pull the output down to ground, and that's because the only way to get a NAND gate to have a 0 output is if all the inputs are 1, right? And then the PMOSs are connected in parallel, meaning that if any of the inputs are 0, then that's enough to pull the output up to VDD. Now you'll notice that this is the difference between propagation and contamination time comes from this, because if you just turn on one of these 3 pull-up transistors, you only get an effective resistance to VDD corresponding to one of these guys. But if you were to turn all 3 of them on simultaneously, you'd have more drive power. You'd only have 1/3 of the resistance of an individual gate, because you'd have 3 of these resistors in parallel pulling up, right? And so the contamination would be like, for example, if you had if you had all 3 inputs go low at the same time, you'd activate all 3 of these guys pulling up at the same time, and you'd get less resistance. And the resistance, the less resistance will give you a better pull up time. Whereas if you just turned on one of these guys, you'd have a slower response. So that's the reason why contamination delay and propagation delay are different. Okay, so now the idea here is that you have to select sizes for these guys. Now, when I was designing chips back when I was in grad school, we generally would, whenever we designed a gate library, we would always just use minimal size for all these transistors. meaning that I would have just used a size 2 for the PMOSs and a size 1 for the nMOSs. That's how I would have done it. That's how I've done it. But that was not ideal, because if you want this gate to be balanced, you have to be aware of the fact that you want to try to balance the pull up and the pull down. So in this case, you have the option as a designer to make, for example, the nMOSs 3 times minimal size. That way they'll have a resistance value of R/3, meaning that the effective resistance for pulling down when all 3 of these guys are on is just going to be 1. So you'll have a resistance for pull down to be as 1, right? But on the other hand, on the pull up, you only need to have 1 of these guys on. So even if only 1 of these PMOSs were pulling up, if they're size 2, then you also get an effective resistance of 1 on the pull up as well. So I tried to show that here, like the resistance for the P is 2 divided by P. The resistance for the N is 1/N. So if you want to have the same resistance pulling down as pulling up, at least in the case where, for example, you have, all 3 of these guys pulling down versus just 1 of these PMOSs pulling up, if you want to balance that, then you can select sizes of 3 for the nMOS and 2 for the PMOS. You don't have to do it that way, but this is one way to try to balance the pull up and the pull down strength. Okay, so let's say we do it that way. Okay, so now we need to come up with an RC circuit for this guy. So you can convert this into a circuit that has all the parasitic capacitances on. So each one of these gates would have, all the gates of the nMOSs would have 3C, and all the gates of the PMOSs would have 2C, right? So you got, 2C, 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 3C, 3C, 3C. And then likewise, you have the, the source and the drain capacitance is 2C for the PMOSs and 3C for the nMOSs, right? Now, as I mentioned a little while ago, some of these capacitors you can eliminate if both terminals of the capacitor are connected to VDD or both terminals are connected to ground. So basically, it means that all of the PMOS source capacitors go away. So that would be these guys, right? So the source capacitor, source, gone, right? Likewise, of the bottom nMOS transistor, you have a source capacitor, that's also gone. So you can eliminate that. So what you're left with is the gates, right? So 3C, 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 and you can combine those with the gate capacitance of the PMOSs. So together, each input to this gate has a capacitance of 5C, which is 3C from each of the nMOS and 2C from each of the PMOS. So there's a 5C capacitor coming into the gates. Now, the output, sorry, let's come back to that in a minute. So the source capacitors of each of the nMOSs stay, except for the bottom one, rather. So there's a 3C and 3C there those are the connections between the between the first and second and third of the nMOSs that are connected in series. You still have those source capacitors there, right? Then if you look at the drain capacitor of the first topmost nMOS, that is going to be combined with the drain capacitors of each of the PMOSs. So you end up with 3C plus 2C plus 2C plus 2C. You end up with 9C, 3 plus 6, on the output of the gate, because you have to add together all of the drain capacitors of all the transistors that are connected to the output. So, you look at the output wire, there's 3 PMOSs and 1 nMOS, so that adds up to 9C. So you end up with this equivalent circuit. Okay, so now we want to figure out what the delay is if we connect this guy to another guy, another gate, right? But before we talk about that, we got to talk about how you calculate the how you calculate the delay. So previously, I told you that you just basically take the resistance and the capacitance, like for example here. And that worked here because you had one resistor. This is two inverters connected. You had one resistor connected to a bunch of capacitors, in parallel, right? There's three of them there, right? And so that was just R times 6C. But when you get into these more complicated circuits, you end up with a circuit that has multiple resistances with capacitors in between. And so how do you? It's more complicated. You just can't take you can't add up all the resistances and all the capacitances and multiply them together. You need to consider the topology of the circuit. And so for that, you use this thing called Elmore delay, which is where you basically consider the circuit like a tree that has branches. Where's the branches? The branches are where these little splitting points are between the resistors and the capacitors. And then you calculate the delay starting from the voltage source, and you go through and you calculate it to each of the leaves of the tree. So the voltage source, first of all, what am I talking about there? Well, that's either the ground if you're pulling down. So if you've switched down the pull down network and you're pulling to ground, that's the ground. Or it's the VDD if you're pulling up. So that's your voltage source, is basically just ground or VDD. And then you can calculate the RC delay to the first capacitor, right? So R1, C1, right? But then once you go off that branch, you got to go through that second resistor, right? So for that, you have to add together the total resistance you see from the voltage source to that second branching point here, right? So you have to add R1 plus R2 and then multiply that by C2. And then you have another branch, so you have to consider all three resistors that are in series there, 1, 2, 3, multiplied by C3, and so on and so forth. So you have to consider, you start at the root of the tree, which is the voltage source, which is, again, VDD or ground, and you have to multiply the resistance times each capacitor, but the resistance is calculated as the total resistance seen between the voltage source and the capacitor in question, right? Okay, so how does that relate to the gates? Okay, so let's take the 3-input NAND example again. So we want to calculate the worst case rising and falling delay of a 3-input NAND driving H identical gates. Now this is a little confusing because when you have an inverter driving other inverters, it's nice and simple because each inverter has one output, each inverter has one input. But in this case, we're talking about 3-input NANDs. So when you have a NAND driving other NANDs, are you talking about fanning out? Are you connecting to all the inputs of all the NANDs? Well, no. In this case, we're just going to have one NAND connected to H other NANDs, but for each of those, only one of their inputs, as shown in this picture here. So notice that this gate is only driving the top input of those guys, right? Okay, so you have to calculate the rising propagation delay and the falling propagation delay. So for the rising propagation delay, you're turning on the one PMOS. One PMOS, right? So you're turning on one PMOS that has a resistance of R. What happened to the other PMOSs? Well, we're going to ignore them for now because we're calculating the worst case. So we're assuming that we're pulling up with only one of the 3 PMOS pull-up transistors. So we're going to forget about the other 2 for now. We will consider them when we calculate the contamination delay. But because this is the propagation delay, I only care about one of the 3 pull-up transistors. So that's an R, and then you have your output, Y, and we know that the output net is connected to 9 9C, right? But that 9C is only capacitance from inside the driving gate. But now you have to add the input capacitance of those H copies. And we're only doing one input on each of the three. So we know that each input to the NAND gate, each input has a 5 units of capacitance, right? Remember, we had 5 units, right? So each one of these guys has 5 units. Why? Well, there's 3 units that's the pull down nMOS, and there's 2 units from the pull up PMOS. So together, there's 5 units of capacitance there, right? So so the total capacitance on the Y net, the output, is going to be 9, which is the internal capacitance from the driving gate, plus 5 times H, which is H copies of the gate we're driving, but only one input each, and each input is 5. So 9 plus 5H, C, right? Now, we have all this capacitance and resistance on the pull down network, right? But we ignore it because we're not pulling down. Now you might say, well, wait a second, hold on. I mean, you're still considering the drain capacitance of the top nMOS. Right, I am, but I'm ignoring all the other nMOSs because they're connected in we don't care. We're not pulling down. So yeah, so that's it. So the total rise in the time is 9 plus 5H times 5H times RC. The R comes from the driving resistor, and the 9 plus 5H is the capacitance of the output as well as the inputs of H identical gates. Okay. Now the pull down, the fall time is a little bit more complicated though, because now we got to use the Elmore delay. We have to use the Elmore delay because remember we've got three transistors in series. So now we've got this kind of more complicated system where we've got to go through each of the transistors and consider each of their diffusion capacitances separately. So for the pull down, where do we start? Well, you start at the voltage source. That's the root of the tree. So we got to start at the bottom at ground. So starting from ground, you go through one resistor for the first, I should say the bottommost nMOS, which has an R over 3 resistance. Why? Because it's a triple sized transistor. And then we multiply that by its drain capacitance, which is 3C. So R over 3 times 3C, right? That gets us to the first branch point. Then the next branch point, we're going to have the resistance is going to be the first R over 3 plus the second R over 3. So we got to go through both transistors, and then we multiply that by its drain, sorry, its source, it would be its drain capacitance, so 3C. So R over 3 plus R over 3 times 3C. That gets us to the second branch. And then the third branch is R over 3 plus R over 3 plus R over 3. And then we multiply that against the output capacitance, which includes lots of stuff. It includes the drain capacitor of the nMOS, the source capacitor, the drain capacitor of the nMOS, the drain capacitor of the PMOS, and the input capacitors of the other gates. All of that stuff is combined in this 9 plus 5H times C. So when you evaluate this whole thing, you simplify this expression, you end up with 12 plus 5H times RC is the total falling delay. So, notice that it's kind of funny because like, obviously the falling time is going to be greater than the rising time. By a factor of, 12 ninths, I guess, or right. But that was done even after we sized these transistors. Like we sized these transistors to try to balance that, but yet they're still imbalanced. Sorry. So yeah, the fall time and the rise time are imbalanced, but that's okay because that's the worst case, right? Now we can calculate the best case rise and fall propagation delay. That's the contamination delay. So in this case, it turns out that the fall time is not going to change, right? But because I got to go through all three of those nMOSs no matter what when I pull down. But when I pull up, I can actually be faster if I turn on all three of those guys, in which case the effective resistance is only R over 3. But that actually, that actually imbalances things even worse, right? Because now the rise time potentially is even faster compared to the fall time. But that's how it goes with these things. Yeah, so there's 3 resistors in parallel, so the effective resistance is R over 3. Okay, so in practice, I can tell you that nobody ever uses a gate in an ASIC with more than 3 inputs because of this problem. Generally speaking, an ASIC cell library, a gate library, you might get some 4 input gates, but generally speaking, they're limited to 2 and 3. So if you need a gate with more inputs, it's better just to combine smaller gates together to get Boolean functions with more inputs. Okay, great. All right, so that's part 1. Now we're on to part 2. This should be hopefully faster. Now we're going to talk about wires. So chips obviously are comprised of transistors and wires. The wires are called interconnect. It turns out that the wires are just as important as transistors in the way that they impact performance and the power. So wires are laid out on top of the active layer. So you'll have on the bottom in the substrate, you have your transistors, and then you have layers of wires that are built on top, and each layer of wire is separated by glass, silicon dioxide, which isolates the wires from themselves so that they can cross over one another without touching, because there's that layer of oxide. If you want to connect one layer to another layer, you use what's called a via, which is basically just a hole in the oxide that allows a connection to be made from an upper layer to a lower layer. So the wires have these kind of dimensions to them. They've got obviously length. That's just how long the wire is, how long you want to run it. The length will be determined by how far away the 2 gates are that you're connecting. The wires also have a width. Now the width is usually set as a technology parameter. So like they'll have a minimum width, and generally speaking, you use the minimum widths. Now each layer will have a different minimum width. So as you go up in the layer stack, the wires will be wider. The ones towards the bottom are thinner. Then you have a minimum spacing in between wires. That's called a design rule. And so when you design your chip, you have to keep them spaced apart. It's the same way with circuit boards too. Circuit boards also have a minimum spacing requirement and a minimum width requirement. But then you have a thickness, which is something you don't see when you design a chip. When you design a chip, you design it from the top down, so you only see the top. You don't see this dimension, this thickness dimension. But it's a parameter of the fabrication process. And then you have the height, and the height is how far the wire is from the layer beneath it and above it. So you have this thing called aspect ratio. Well, first of all, you've got pitch, which is the width plus the spacing. So it's how far each wire is apart from their center points. And then the aspect ratio is the thickness divided by the width. And you might be surprised that modern processors have a aspect ratio of about 2, modern processes rather, meaning that they're twice as thick as they are wide. And to prove that to you, this is actually this is a cutaway picture of the Intel 90 nanometer process. So this is like looking at a cross section of the chip. So the Intel 90 nanometer process had 6 metal layers, and you can see that the metal layers get wider and thicker as you go up, and you can also see that they're thicker. They're about as thick as they are. Actually, the metal 5 looks like this is a minimum width wire, and it's much taller than it is wide. So you can see the aspect ratio is greater than 1, maybe even 2. And then this is the 45 nanometer stack. You can see this one has 8 metal layers, and these are also very tall. You can see that some of these layers have the vias, that actually contact, through the layers from one layer to another. This is how you go from metal 6 to metal 5. You just create a hole in the oxide, and then the metal flows in. Okay, so yeah, so the bottom metal layers are usually for very short runs, like within cells, and then as you have to route wires to farther away regions on the chip, you use higher metal layers, and thus the wires will be thicker. So, for example, you might use metal 2 for vertical routing and metal 3 for horizontal. You might alternate vertical, horizontal, that way it keeps everything separate. When I used to design chips, I used to do it by hand, and so I just sort of, I didn't follow any kind of guidelines for which metal layer to go which way. It was kind of ad hoc. Anyway, modern processes have a 6 to 10 metal layers. Although, to be fair, no one designs chips by hand anymore. It's much more automated than it was when I was doing it. Okay, so why are we talking about wires? Who cares? Well, it turns out that wires are a source of delay and power consumption. Wires have capacitance, and they have resistance, and they have inductance. Resistance is like, if you have a narrower wire, it impedes, like if you think of it like a pipe, right? If you have a narrower pipe, it impedes the flow of current. If you have a wider pipe, wider wire, you have less resistance. Capacitance, though, is like having a trough underneath the pipe that the pipe leaks into, and so you have to fill the trough before you can start sending current down. And inductance is like having a paddle wheel in there that resists changes of flow, right? Now, luckily, on a chip, inductance is usually negligible, so we won't consider inductance. In fact, I don't know if this has changed, but back in my day, when I used to do parasitic capacitance in parasitic extraction, where you would take a layout and you would extract all of the parasitics in it, they didn't even extract inductance in anywhere on the chip. Now, inductance, though, is much more prevalent on longer wires that go off chip, right? So like if you have like circuit board traces, you're going to have to model, generally speaking, you model the inductance for those. But for anything on chip, they generally don't model inductance. That might be changed now. It's been a while since I've used the tools. Maybe they do, although at the time, back in the late 90s, early 2000s, the conventional wisdom is that it wasn't tractable to extract inductance. There's no way, it would be way too expensive. It would take too much time. And you wouldn't get much back because there's not much inductance anyway. Maybe that's changed now with these deep submicron processes they have now. Oh, hold on. I did. Oh, yeah, you're right. They are frozen. Holy cow. What is going on? Sorry. Thank you. Thank you. Thank you, William. I don't know why they're frozen. Let me reshare. Oh, okay. Hold on. Yeah, sorry. Thank you. I think the reason why they're frozen is because I never switched slide deck. Sorry, it's my fault. Okay, so let me go back here. So again, I interconnect. Yeah, these are the wire geometry, width, spacing, length, thickness, height. You got your metal layers. That's a picture of the actual metal layers. And then this is the way that this is the slide about modeling interconnect. Okay, so I'll just cover this last slide, and then I'll end class a little early so you have a chance to go take the quiz because that's due today. I'll go over these slides again on Wednesday. Especially since you guys didn't see the slides, the first few slides. Okay, so anyway, so there's not much inductance in on-chip wire. There is on off-chip. We're just going to talk about on-chip wires for now. On-chip wires have resistance and capacitance. They have capacitance to the wires above and below and to the sides, and they have resistance because there's this resistance that's inherent inside the wire metal, the material you make the wires out of. The problem is that the resistance goes all the way down the wire, as does the capacitance. But if you want to model this, you have to break up the model into segments. Like, for example, you can't just say, I want to model the resistance all the way down the wire and the capacitance all the way down the wire, because obviously as you go down the wire, the effective resistance and capacitance changes. So you have to use a lumped model where you take the wire and you decompose it into lumps, where each lump is a separate. Yeah, sorry, this is where we want to be. Is a separate resistor and capacitor. And there's different ways to actually build the lumps. You can use what's called the so-called L model, which is one resistor and one capacitor, and then they have the pi model and the T model, which the pi model has one resistor and two capacitors, and the T model has two resistors and one capacitor. It turns out that the pi model is the one that's most commonly used because it's generally the most accurate as compared to the other two. And then the other nice thing is that, actually all of these are amenable to the Elmore delay model, which is what we talked about for the gates. Okay, so yeah, so I'll go ahead and just end it there. If any of you have any questions about the quiz, send us an email. On Wednesday, we'll continue with this lecture and hopefully finish it up. It's not as long as as part one, and then we'll start on the next week. We'll start on the next unit, which will be System Verilog. So thank you, everyone. I'll see you on Wednesday.